We've got a variety of measurements. So there's 4 major kind of categories where we can go through and define our different measurements. So we've got distances or lengths, mass or weight, volume, and time. So when we go through to report a measurement, we take down the number, but more importantly, we have to take the unit. Because if I just write down a number, say 75, what does that 75 mean? Silence is a pretty good answer to that. We have no context of what that means. Okay? So you're going to continue to hear this throughout the semester, because what I will ask you to do is give me the unit. The number really doesn't hold much value. The unit will solve the question for you. The number will only mislead you and take you down the wrong path. Okay? So watch out for that. So what are some units that we could potentially get in here? Distance or length. What's a unit? Meters. Centimeters.
Inches.
There we go. Let's throw in some weird ones there. Inches. Foot. We can do miles. We can do kilometers. Stop suggesting, because I'm going to stop writing with that. Okay. So we've got a bunch of different potential units that we could use for these. Okay. Well, which one is the unit for distance?
Meters. Kilometers.
Okay. Why meters versus kilometers? Why would you use kilometers?
Well, kilometer is
That's a fair guess.
it's like this. A meter is like the base for all of those.
Okay. So this is going to come down to what we're going to be specifying. If we want to measure the distance between here and your house, is measuring it in meters going to make sense? No, you're going to end up with a really large meter value. Okay. The human brain does not deal with numbers well. Okay. So we want to make our numbers as small as possible. We'll keep coming back to examples of counting through 1 through 10. Within that range, we are pretty good at dealing with number size. As soon as we exceed the number 10, we have problems comprehending that value. Okay. The larger you get, or the further away from 10 you get, the harder and harder it becomes. So what we end up doing is changing our unit so that we can change the number that we're associating with it. Okay. So if it is, let's say you're really close. Let's say it is 12,462 meters to your house. Well, 12,000, I don't know really how much that is. That's too big. So we could shift to a different unit system. We could shift to kilometers. And for those of you that know that conversion, it would become 12.462. I still have all the numbers, but at least the biggest number I'm working with is 12. I know what 12 is. I can handle that. 12,000 was a little bit too large. Okay? And yeah, you're like, oh, that's dumb. Everybody can understand those numbers. That's complete nonsense. That's not true. Okay? You cannot understand those numbers. As soon as you're down to 10, you're fine. Okay? So we can change that unit to represent better what we're looking at. If we're looking at the distance from here to your house, kilometers makes sense because it brings the number down into a more sensible position. Okay? So kilometers makes sense. Now let's measure the length of the pencil. Why would we not use kilometers?
Because it's huge.
Kilometers is a massive distance. It doesn't make sense to use that unit to measure something so short. So we'll change our unit depending on the size of the object we're looking at. Okay, and this happens with all of these units. We'll change different units to get to different sizes. Not only do we change different units to get to different sizes, but you'll notice that I grouped the meter, centimeter, and kilometers all on top of each other because they all end in meters. The base unit that we end up using for most science when we're looking at distances is meters, and I'll refer to it as a base unit. It's just the shortened version of it. Okay? Now, how do we adjust from that? Do we go to a value that's larger than meters? There's our kilometers. Do we go to a value that's smaller than meters? We've got centimeters. How do we know that we're going larger or smaller? I don't see a decimal point necessarily associated with those yet. What about centi says it's getting smaller? You have to know what centi means. If you don't know what centi means, you don't know that it's getting bigger or smaller. Okay? So you have to now associate some meaning on top of that. Okay? So it's not just, oh, here it is. Now we know it's getting bigger or smaller. You have to memorize some more information. Okay? Why would I have separated out inches, feet, and miles? Those are in a different measurement system, but they do kind of roughly correspond. I didn't do a very good job matching them. Centimeters and inches, we could kind of say is our rough comparison. Meters and feet, okay? And kilometers and miles. Sort of rough approximations on our comparisons between them. Why are meters, centimeters, and kilometers so helpful? They change based off of powers of 10. Okay. How do inches, feet, and miles relate to each other? Okay. Well, how many inches are in a foot? 12. Okay. Well, I can still deal with 12. That was a reasonable number, so that makes sense. So we go by factors of 12 instead of 10. That's not a big deal. Feet and miles. Should be 12, right? 5,000. What? Where did we come up with that goofy-ass number? Where did we come up with that number? Okay. It's a completely arbitrary system. Both systems are completely arbitrary. Okay? One, someone went through and said, I'm going to define a meter to be this length, and now I'm going to say powers of 10 to change off of that. The other system said, I'm going to define an inch to be the length of my thumb. And then my feet are bigger than my thumb, so I'm going to also define a length to be feet. Oh, and look, there's roughly 12 inches, 12 of my thumbs in my feet. Okay? Well, now when I count out these really big distances, well, I'm going to define that to be a mile. And there's roughly 5,000, whatever your number was, feet in that mile. Completely arbitrary and completely nonsensical and dumb. Okay? Thankfully, what system do we use most commonly in the U.S.? No. We use the dumb system. Okay? But as scientists, we can say, screw off dumb English system, and we can switch to the metric system. So nearly all of our conversions are going to run through the metric system. So we're looking at meters as our base unit for our distance. Let's just clean all that up. What about mass? Do we have different measurements or units for mass? Grams, pounds, kilograms. Oh, interesting. Gram, kilogram. Meter, kilometer. The kilo is showing up again. Okay. That's because that's a smart system. Okay. What are the other units when we look at our American system with pounds?
Ounces.
Ounces. That's a good call. I didn't know that one. Ounces, pounds, tons.
Gallons.
Gallons isn't a mass, though, unfortunately. Okay. So our standard unit that we're going to be using for this class for most of our measurements for our mass will be grams. That's an M that I somehow screwed up writing. Volume? Liters. Okay. We could use gallons. We could use quarts, pints, cups, tablespoons, teaspoons. Okay. All of those are valid measurement systems, and depending on what you're working with, you may want those units. We aren't cooks. We're chemists. We're dealing with the liter system. Okay. Just to throw this out here, just because I think it's kind of irritating. What's the difference there? It's just a swap in the spelling. Okay. Depending on English or American or English, I guess we should say. Okay. You'll see there's different spellings, so don't stress on that. Typically here you'll see it as RE. Not RE, the other one. ER. Time.
Minutes, hours,
Okay.
seconds.
Time, we can kind of bring in this balance of our metric system when we look at seconds. Okay. But very commonly, time also breaks down into minutes, hours, days, right? Or horses. Days. And we kind of expect you to already know those conversions, right? So how many minutes are there in a second?
How many seconds are in a minute?
How many seconds are in a minute? Just
60.
testing. It's 60. So we're not using nice powers of 10 within those conversions, but we do kind of expect you to have already known those, okay? So we don't stress as much on those. Okay? So these standards were created to quantify, and we defined them as those. Okay? And that's our metric system. Okay? Most science uses the metric system. Okay? And it's an important distinction to make that every single one of these units is completely and utterly made up. Okay? Nobody came down from heaven and said, this is a second. No. Some random person said, no, that's a second. Somebody else said, well, no, I think this is a second. The first one killed the second one, and we're stuck with the first one. Okay? It's as simple and basic as that. Someone said this is what it is, and we decided to listen to that person. Okay? Why would we decide to have a standard unit system? So that when I do an experiment here, and you do an experiment over there, and we compare our results, we can compare them quickly and easily, because they're in the same system. Okay? So, measurements and uncertainty. Okay, this is kind of an important observation now. This is much more relevant for the lab, a little bit less relevant for the lecture, but this is how we get into sig figs. Okay, so if we look at distance, we've got a ruler here, which is marked off to 10 centimeters. What is the length of that silver block, which is supposed to be a rod, but let's just call it a silver block? Okay, 4.2. Okay, and right away I'm going to tell you, you're wrong. Why are you wrong?
It's not exact. Because the two have.
Someone over here said it. You need the unit. Okay. Now the question becomes is, did you report the proper numbers? Okay. Well, in our measurements, we always include our obvious digits, okay, the ones that guaranteed. We will always add one extra digit. Okay. That one extra digit is an educated guess. We have a little bit of information about that place, so we're specifying that information. We don't include another digit. Why not? Well, if one is a guess, what's the next one? A guess on top of a guess. So how accurate is that one? Not very. What if we had included another digit? So a guess on top of a guess on top of a guess. We're completely making stuff up at that point. So we don't continue to include digits. We can only include the ones that we have some information about, that are either guaranteed values or that we have some educated reason behind. So when we look at this measurement, that ruler's got it marked out by our ones place. Our rod is clearly longer than 4 centimeters. It is also clearly less than 5. So if I wrote 5 there, we'd have a bit of a problem. We wrote 4. Good. Everybody agreed with that. Okay. But is it larger than 4? Yeah. How much larger than 4?
Less than half. Guess.
Less than half. 0.2. It's a guess-ish because it's not 5. I have educated information that it is a value that is less than enough to make the number 4 into a 5, but it's more than to make the number 4 into a 5. Right? So we need to come up with a digit to put in there, and we're going to guess at that value. Is 9 a good guess? Why not? If it was a 9, we would expect it to be closer to the 5. So it can't be a 9. Okay. How about a 7? 6, 5, 4, 3, 2, 1. Okay. We've got 4.1 all the way up to potentially 4.4. So we need to guess at that value with one of those. Which one do we pick? It's a guess. Who cares? Pick one. Okay. We picked 4.2. We now have reported that information out so that somebody, when they look at that number of 4.2 centimeters, knows a rough idea of how accurate we are in measuring that device. Okay? Questions about that so far? If I want to report more information about the length of that rod, what could I do?
Measure it.
I want to use a ruler that has more markings in it because those more markings will allow me to then quantify to larger detail. So if we switch this up to a new ruler, what is the length of our device? Or our rod? 4.2. Not quite.
It's 5 centimeters.
5. I was trying to check the number. And then our centimeters. Okay. We've now shown, just by writing that number down, that the device we used, ruler B, has more information in it. Okay. If this was your paycheck, which one do you want to be used? The one that's a little bit more accurate. Okay. You may run the risk of losing a couple bucks if you went to a less accurate device. You may run the risk of losing maybe a couple bucks if it was overestimated. But then you also don't run the risk of losing that money when it's underestimated. Okay? So we're trying to determine something about the precision of our device. Okay? The more decimal points, the more precision we get within it. Kind of make sense? Okay. The next part of this, in very small letters at the bottom, we should specify an uncertainty. Your very first lab will talk about that, which I think is next week. You haven't started. This week is a safety video, right? Yeah. Okay. So next week you'll look at uncertainty. Well, what is the uncertainty? Okay. With ruler A, what did we get for a value? We said it was 4.2 centimeters. Thank you for following up on the units. Okay. And when we broke that down, we actually said that could have been anywhere between 4.4 all the way down to 4.1 centimeters. It's a lot of extra information to write. So what I can go through and do is with that 4.2 centimeters, is I can actually we can even just leave the unit there. We can say plus or minus 0.1 centimeters. So this measurement with that uncertainty now tells me that my value is between 4.1 up to 4.3. Darn close to what we had guessed as possible values. That uncertainty now gives me a little bit more information. Okay. I can use that to then propagate error if I wanted to. Every time you take a measurement, you should be reporting the uncertainty. Okay. That said, there is only one lab, likely, that you will be reporting the uncertainty for. And that would be next week, the very first lab. After that, you will stop reporting the uncertainty. Why? That's really tedious to write plus minus whatever your value is afterwards. How do you determine what that value is, the plus minus, 0.0 or 0.1? You're looking at the values that were possibles. Well, how do you know they're possibles? We just looked through and used the class as kind of a rough supervision of those possibles. Okay. The uncertainty applies to the device. Ruler A will always carry that uncertainty. It doesn't change depending on the measurement. It is always that value. Okay. Well, if it is always that value, wouldn't it be nice of the manufacturer that made that ruler to give it to you and say, hey, the uncertainty is this? Wouldn't that be nice? Yeah. Guess what? If it's a reputable distributor of that device, they tell you the uncertainty. It says in it what it is. Okay? So that way, when you go through to take measurements, you know to always report your values to that accuracy. Okay? For instance, this is a fun one now. Let's take a look at a quick eraser here. Let's go through and change the size of the block. That's not quite perfect. try that again. Let's go with that. Ignore all this other stuff. Pretend that's not there. What is now the length of my cylinder?
4 centimeters.
4.0.
Thank you for giving me the 4 centimeters, but now I'm going to call you out for it. How many digits did we report to? Just one.
4.0.
You have to include that uncertain digit. We would have to report this as 4.0 because our device measures to that place. We have to include the guess digit. The 4 was our exact value. Those of you shouting out 3.9, it's not that that was wrong. That is within the uncertainty of our device. Right? But with 3.9, you look at it and you write 3.9. When we said 4 centimeters, what would you write?
4.0.
What would you have written? Come on, be honest. You would have written 4 and then said centimeters. You would have left the 0 off. By removing that 0, you've lost information in the measurement. You are not allowed to just give up information. Okay? So you have to report that extra 0. Yes?
Is that extra 0 on here significant?
We haven't addressed significant figures yet, but this is part of dealing with measurements. Once we've figured out how we deal with our measurements, then we'll address sig figs and how we propagate those. But you're right. This is going to become important. Is that digit considered a significant digit? Based on the rules? Yes, that is a significant digit.
Unless there's
Okay. And we'll talk about how we apply those rules in a little bit, but yes, that is a significant digit, which is one of the reasons why we had to write it. Okay. But again, how would you know you had to write it? You can't just say it's significant and now write it. Your measurement has to tell you it. Yes?
If you would have put 4.20, would that have been wrong?
If I had written 4.20, is that now wrong?
guess and a guess.
That 0 is a guess on a guess.
So the
Okay.
second one
That-
is always a guess?
Not the second ones. That's where you got to be careful. If we go back to this measurement, we are guaranteed that 4. We know it's greater than 4. What do you know about that 2?
It's not.
It's a guess. Okay, so that's a guess. What do you know about that 0? Well, if the 2 is a guess, what does that make the 0? A bigger guess. If you're guessing on guessing, that's a really bad idea. You should just give up and just pick a letter or a number. Okay? So if you write 4.20 with the ruler A, it's wrong because you have no information about that third value. Okay? So it depends on the device. When we move to ruler B, we have information about that third value. Okay? Make sense? Okay. It's fair to say it doesn't. Okay, because it is a confusing topic. Other questions? Okay. Mass measurements. Mass is different from weight. Weight is dependent on gravity. We'll just leave it at that. So when we're talking about things, we will be massing things. We'll be using a noun to become a verb. That's okay. Okay, so we will need to obtain the mass of things. We've got a variety of ways to determine the mass. Okay. You've got what's known as the triple beam balance. A few different versions of those, both in A and B. Okay. Fun and dandy little devices allow you to compare the whatever object you're putting on there to a standard mass built into the equipment. You would have to read the equipment just like you would read a ruler. Okay. So your measurement is going to be dependent on the accuracy of the equipment. The fourth, that's third. It's the third thing because there's only 3 things there. C is an electric balance. The electric balance does the exact same thing as A and B. It records or it compares the mass of what you put on there to an internal standard to it. Okay. What's nice about the electric balance is it then reads the result for you. Okay. So there is no looking at it, where's the line fall, all this stuff that you would do with a ruler or the triple beam balances. It is now just what number does it spit out. So if it spits out 1.000 grams, what should you write in your notebook? 1.000 grams. You have to report the exact same thing it spit out. Why? Those zeros are significant. It is telling you what those values are. It's not guessing, it's telling you. Where is it guessing? That is its guess value. That last value. Okay, in this case, it's a 0. Okay? It won't give you any more than that, well, depending on the accuracy of the balance. Okay? If you move up into, say, organic or 152, you'll notice the balances will read out something more along these lines. What happened? It got more accurate. I got an extra 0 there, an extra place. Okay? Why do you not get to work with those?
Because we can't be that precise.
Because we're lucky.
Price tag. Adding that 0 adds an extra $500 to $1,000 to the device. Okay? If we add another 0, adds probably $1,000 to $10,000. Okay? The precision of the device, it has to internalize and make sure it's accurate out to those values. It doesn't just scale linearly or all the same price. If they're all the same price, we'd have amazing balances in all of our rooms. But we have to get progressively more and more accurate, which means we have to get more refined in how we look at things. Okay? The scale of those numbers might be off. Don't quote me on that. Okay? But it does get more expensive, significantly. Okay? So, when your balance spits out a number, you write down that full number. You don't ignore zeros. Okay? There is a nifty little video here, which I think I'm not going to click on to watch. But if you go through and check out that link later at home, I think it's kind of fun. They determined, or they've now made, a 1 kilogram mass. That it will become the standard for all 1 kilogram masses in the world. And they made it out of silicon. They made a perfect sphere, which seems kind of insane. Okay? The discrepancies in the height on that sphere are on the order of like 3 or 4 atoms thickness. Okay? You compare that to the planet Earth, you're looking at the order of several million atoms thickness difference. Okay? So the Earth is not very spherical in comparison to what they came up with. It's pretty impressive. Just kind of a neat little story. After that, we've got volume measurements. Volumes are typically used to measure liquids. Forgot to say that about masses. Mass and balances are used to measure solids, typically. We can use volume to measure our liquids because they fill whatever object they're in, so we can design an object to measure each of those solids or those liquids through a varying devices. Okay. Within those, we have to be aware of how we record our measurements. You'll notice none of these are digital. Most liquids, oof, that's a pretty ugly liquid. Most liquids, you'll notice, will form kind of a curve on them. You need to record your value at the bottom of that curve. That curve is known as the meniscus. Okay. So all you will do is report whatever value or where that line seems to cross your device. Okay? Some things to watch out for. Graduated cylinders tend to record where your 10, say it's a 10 mil graduated cylinder, is up top and the 0 is at the bottom. Why do they measure it that way? Where do you get the liquid out of? The top of the container. So we fill to the top, and that's our full volume. You will use at the end of the semester something known as a burette. If we look very carefully at the numbering at top is 0, and the numbering at the bottom is 50. We've inverted how we number. Why? The burette pours out the bottom. Okay? So it's an adjustment on how you look at it. It's going to change how you read the device. So you'll have to be careful when that lab comes around at the end of the semester. Okay? Other questions? I know, you didn't have any questions. I said all that. So, significant digits. Okay. Now that we've got our measurements, those measurements, everything in our measurement is a significant digit. And in some cases, we have zeros that are considered significant digits. But what if you aren't making a measurement? What if I'm just giving you a number and saying, tell me if it's significant? Well, your response should be, I'm in lab, I'm making a measurement, I'm recording all the significant digits, I don't need to worry about counting significant digits because the device tells it to me. And you have a very valid point. Okay? Unfortunately, you need to be able to interpret sig figs with numbers that aren't measurements taken by you. You have to take my word for it or the textbook's word for those measurements, so you have to be able to interpret what they have done. So it's interpreting somebody else's work. When we use those interpretations, we then also have to be able to manipulate them in certain mathematical functions. Okay? When we use our mathematical functions, that can have an effect on the amount of significant digits in your calculation. Okay? So before we can even get into the mathematics, we have to make sure we understand how to count our significant digits. Okay? So if we looked at these numbers up here, okay, our significant digits, and everybody was puzzled by this to begin with, we have 1, 2 sig figs, 3, 2, and 1. And we got a lot of whats, and weirds going on with that on Tuesday. And yes, I agree. There is a whole lot of whats, and weirds going on with that and trying to understand what's going on with it. And ultimately, what happened, or what was different in each of those, is how we counted the zeros. Okay? In some cases, the zeros counted as significant digits. In other cases, the zero did not count as a significant digit. What else changed in the course of looking at these numbers?
Placement of the decimal.
Okay. Not even just the placement of the decimal, but is it even there? Which might be what you were saying by placement. Okay. Is there a decimal point or not? It turns out to determine the significance of a zero, we have to know something about the decimal point. Okay. That is how we decide the meaning of our zero. Because in some cases, all the zero is meaning is don't put anything in this location. For instance, if we look at that first number, what is it? 10. And yet it only has one significant digit. That one significant digit is the 1. So I've had a lot of students say, well, if it's only one significant digit, then just don't show the 0, and then it's simple. Except, what's my number now? 1. But it's 10, not 1. How do you know it's 10? What if I had gone through and done something like this?
Or you can tell it's 10.
How do you know it's now 10?
It could be 12.
It could be anything above 10.
Yeah.
That
Whoa.
decimal point tells us that the 1 is located in the tens position. Okay. So we know our value is some number 10, between 10 and 19. I still don't know what this number is. Okay. But my value is somewhere between 10 and 19. Okay. By showing those lines, I'm now showing where the significant digit is, and that implies meaning. We could go through and show under every single measurement a line representing the place, okay, ones, tens, hundreds, thousands, and then writing our corresponding digit above it. That is perfectly acceptable. We could go through and do something like that. However, most of our mathematics would then look like some weird Morse code system. So we came up with something else to simplify that. Instead of showing each of the dashes, we went through and said, okay, I'm going to put a 0 there. Now I know in the ones place, there isn't anything, and in the tens place, there's a 1. But am I really saying that there isn't anything, or what I'm saying is don't put the 1 there? Okay. Two meanings for that 0. One, a numerical value, I'm saying it is not 1 through 9. And the second meaning, I'm saying don't put anything in that place. The 0 acts as a placeholder, a blocker, so that I know that the 1 belonged in the tens place. I did see it.
I was going to say, is that 0, would that be considered like a guess?
We don't even want to bring in the guess yet necessarily either. Okay. So at this point, what we're trying to do is distinguish between what is the meaning of a 0. Okay. Which is fun, because in mathematics we spent a long time determining what 0 was, believe it or not. And we finally got to it that 0 meant the lack of anything. Okay. There was no 1s, there's no 9s and all that, and that's how we teach mathematics. And now what I'm telling you is that's not the only meaning for 0. 0 can also be, don't put a number here. Okay? It's acting as a placeholder. So how do you know that it is incorporating a meaning, a lack of a digit, or a placeholder? That comes down to the placement of the decimal point. Okay? So there are a variety of ways to approach looking at the placement or looking at your sig figs. In the textbook, I think they've got 5 rules. I've had a bunch of people show me, oh, my teacher gave me this list of 5 different rules, and then there's 3 or 4 exceptions. And you read each of the rules, they're all exceptions of the previous one. Okay, which is complete nonsense. Okay? There aren't really any exceptions. These are your rules, which would almost argue is only 2. Rule number 1, your digits 1 through 9 are always significant. There is never an exception to that. Rule number 2 is what is the meaning of the 0? Okay. That has kind of 2 subcategories within it. If there is no decimal point, then for the 0 to carry meaning as a not 1 through 9, it has to have a significant digit to the left and to the right of it. If that is satisfied, then the 0 holds meaning as not 1 through 9. Okay. If instead there is a decimal point, okay, that decimal point helps nail down some meaning and a location of the places. And ultimately, that's what our 0 was trying to do, was figure out the locations, placeholders. The decimal point now starts to bring that meaning into the system. Okay. Now we interpret our 0s, and for the 0 to be significant, it must be preceded by a significant digit. Okay, which means there has to be a significant digit to the left of it. If that is true, then that 0 becomes significant. Clear as mud? You're shaking your head saying no, it's not clear as mud? That means you understand it, right?
Can you write a number to number 3? Like,
What?
follows that rule, like a number? If there's a decimal point, then 0 needs to be immediately preceded.
Okay.
So 4 by a significant digit. to be
So
significant.
let's break them all down. So we wrote down all the answers before. Number 1, did anybody want to challenge any of my answers? Nobody gutsy enough, huh? I've had a few people talking to me in office hours about challenging them. I was still right. So.
But now I don't want to.
That's fine. Okay, so let's go through and look at it. So, first number.
2.
No, that's a 1. What are you guys talking about? 3. It's a 1. And then a 0, and then get... How many sig figs do we have in this number? 3. Why is it 3? Okay, you can shout out the answer. Fair enough. Now let me record that. Okay. We want to go through and break this down as slowly and painfully as possible. Start with rule number 1. Digits 1 through 9 are significant. So underline them. 1 is a significant digit. 2 is a significant digit. I have a 0, so now I'm in this stupid little category where I have to deal with zeros and what their meaning is. So I now have to look at my 2 rules. No decimal point or decimal point. Do I have a decimal point specified? No. which means I'm following rule 2. If there is no decimal point, then the 0 must be controlled by numbers. Dang it, there's the thing. It shouldn't say numbers. Keep forgetting that stupid typo. Significant digits. Okay. To the left and to the right. So let's take a look at our 0. And we look to the left, what do we see?
Significant.
Significant digit. You look to the right, what do you see? Significant digit. What does that mean? The 0 is significant. Now I count my lines. 1, 2, 3. I have 3 significant digits, also written as SF for significant figures. Okay? Next one down. The 1 and the 2 are significant digits. No decimal point. Okay? I have to be controlled both to the left and to the right. To the left, do I have a significant digit? Yes. How about to the right? No. Which means the 0 does not count as a significant digit, and I have 2 sig figs. Okay, and to your question, we needed something for rule 3. So we look at the next number down. 1 and 2 are significant. I have a 0 that I again have to question. I see a decimal point, though. Here's rule 3. I do have a decimal. The 0 needs to be immediately preceded by a significant digit to be significant. That means I have to have a significant digit immediately to the left of it. What is immediately to the left of it? A significant digit, which means 0 is significant. I have 3 sig figs. Excuse me. Next one down. The 1 and the 2 are significant. I now have 2 zeros to worry about. Okay. Which 0 should I look at first? The one next to the 2 is going to be our best bet to look at first. Why? Because it's easier to get to the correct answer if you do it that way. Otherwise, you got to go cyclic. Okay, so pick the number furthest to the left. We look at the 0 there. With a decimal point, I just have to have a significant digit to the left. What's to the left of that 0? A significant digit. What does that make the 0? Significant. We move to the next 0. What is to the left?
A significant digit.
A significant digit. Good answer. You didn't say 0. Okay? The 0 is vague. It's a significant digit. We just identified it as a significant digit, which then makes the 0, that last 0, a significant digit, and we have 4 sig figs. Questions?
What if it was 102.0? I'm sorry, 100.0, I guess.
I can do that.
If that 2 wasn't significant.
102.0.
Or even 100, actually, I guess now. I guess what I'm looking for is to make that 2 not significant. What would happen?
You can't make the 2 not significant. 2 is always significant, 1 through 9.
I mean, changing the numbers so there's not a 2 there, so that number isn't significant, so we can do it.
But it's still,
Okay.
it's still preceded by
So,
a 1,
here.
so even if it was a 0, it'd still be
Let's-
significant.
And we'll do a couple examples there. 100. How many significant digits?
3. Oh, wait.
1.
No, 1.
Why only 1?
How about 100.0?
Because there's no decimal.
Okay, we'll get to that. No decimal point. We have to have a significant digit both to the left and to the right. In this case, I only have it to the left. There's none to the right. I only have 1 significant digit. How do I ensure that some of those zeros become significant? How about I just put a decimal point? Now what happens?
There's 3.
Now there's 3 significant digits. Why? Because of the decimal point, I only have to look to the left, which makes that first 0 significant digit. I take a look at the next one, significant digit. Okay. So I would end up with 3 significant digits. Let's just ignore that number. What happens if I add another 0?
Becomes 4.
I'm just seeing how fast you can count. All those zeros are now significant. Okay. Because they are all preceded by a significant digit. Okay? Questions?
So on that one, like, like Yeah, ton of zeros, all the zeros count, no matter what.
All those zeros will count because the decimal point and we had sig figs in front. Right? So what happens with the next number? There's only 2 sig figs. There's no zeros even to look at, so we don't worry about it. We have 2 sig figs. How about the next number down?
2.
Also, just 2 sig figs. Why do we not count that 0? There is no significant digit directly in front of it, so we can't count that 0. What is the difference between those two numbers?
Really, just to put a 0.
So you can see the decimal better.
It is purely aesthetic. Aesthetic? Prettier. Stick with that. Okay. We only include that 0 because we're trying to draw attention to the decimal point. If you're really going to be honest about how you would write out that number, it would probably be something like that. What did I just write?
12.
Okay. I need your help here. Right there.
Mm-hmm.
Is there a decimal point there?
Yes.
It's not 12. There was a decimal point. Okay. You couldn't tell that. But what if instead of doing a quick decimal point, I'd done that? Now would you have been like instantly 12? Would you have been like, why the hell did you put a 0 in front? Okay. That would have caused you to pause and theoretically look just a little bit closer and say, there is a decimal point there. I just didn't draw it very well. Okay. That is the only reason we include that 0. It is known as a leading 0. Okay. If you don't include the leading 0, you're not necessarily wrong. Just realize who's ever grading it may not see your decimal point and may not give you points for it. If you put the 0 there, it's now a red flag saying there's probably a decimal point sitting in there. Look for it. Okay? Questions about that? Is there a question there? You guys got? Good. I'm going to guess you guys are good. Next one down. 2 sig figs. I've included even more zeros in front. Neither of those zeros are significant because there's no significant digit in front of them. Make sense? Last one? 3. Okay. So, how many quarters are in that picture? Those are quarters. Yes, those are quarters. Okay. So if we were to write down that value, we would end up with 7 quarters, right? How many significant digits are in that measurement? Okay. So it's actually possible there's 7.1 quarters. 6.9? So it's not just one significant digit then, because your measurement, you're saying it's not 0.1. That would be 2 sig figs. So how many significant digits are there? 2. So you're saying it's not 7.01? Okay, well, if it's clearly not 7.01, then that was 3 sig figs, and you told me there were only 2 sig figs. So how many sig figs are there?
Oh gosh. Just had it too.
The answer, infinite. There's an infinite amount of sig figs in this quote-unquote measurement. Okay? That is because it is not strictly a measurement, but an exact value. Okay? When you encounter exact values, they have an infinite amount of sig figs. Okay? And if you thought the last stuff was as clear as mud, I'm sure this is looking like a brick wall. Okay? Yes, the exact values are confusing. Never assume you have an exact value. Okay? The only time that you should know you have an exact value is because you look at it and like, it can't possibly be 7.1. Okay? It is a counting feature that gets you exact values. Okay? How many inches are in 1 foot? How many sig figs? you're already catching on too fast. Infinite sig figs in this measurement. There are exactly 12 inches in 1 foot. How do we know that?
Some guy said so.
There it is. It is defined to be 12 inches in exactly 1 foot. Okay. Super important when we start to deal with conversions. Questions? Okay. So, why do we care about sig figs? So let's take a look at some simple addition subtraction here. Hopefully addition is easy enough that you guys could do this without a calculator. So if you could go ahead and tell me what the answer is to this calculation. And there's a reason I erased all that other stuff. I'm going to apologize for this right now, but you'll understand here in a second. 6, 3, 3, 6, 2. Everybody get that same answer? I don't think you want to agree with him. What different answer did you get? What different answer did you get?
I just. Your grams, so that's what I got on mine. That's it. No, I got that.
115.
So you got a different answer of 115 grams. Okay, now I'm hearing 115.6 grams. Anybody else want to venture guesses out here?
I just, because the grams for the top one is like over more, so you assume that there's like going to be zeros there, so you can carry those down.
That's where we have to be careful. The correct answer, 115.6. Every other answer is wrong. Okay. How did you get the big long 115.63362? You added extra value into the measurement. You went into the calculation and you said that those were zeros. Okay. These are all measurements. Okay. That 3 is what? A significant digit, which we also referred to as our guess value. What do we know about the next number?
It's a really big guess.
We know nothing about it. It is some digit between 0 and 9. What do we know about the next number? Same thing. It is a number between 0 and 9. You assumed by entering it into your calculator as such that those were all zeros. And you got that original number. But those values could have just as easily have been 9s. If they were 9s, the number we get if we go back and change 115.63362, are those numbers different?
Yes.
Yep. Okay. We cannot add information to stuff that isn't there. That means when we report our answer, we can't use the 115.63362. We have to effectively remove the excess information that we aren't allowed to know anything about. And that would be all of our guess columns. Okay? So over here, I'm not allowed to know anything about those values. Okay, so if we go over here, let's do it. Oh man, I didn't line it up very nicely. Okay? If I move up to the number above, I also don't know about those values. Which means I can only report out to that first decimal. Said another way is what's in the red box. The result of your calculation is only as precise as the least precise measurement. Does this mean you should change your calculations? No. Punch it into the calculator, get your number, and now decide what place should I be reporting to. So we would go back to our value and say we can only report out to the, tenths with a TH place. I'd go to my number where I have the tenths place. I would underline it out. That is the number I'm allowed to report. Make sense? Okay. This is why we need to keep track of our sig figs. If we can't count sig figs, then we can't do this appropriately. I thought you were laughing at me, actually. So bless you instead. Okay. Sorry. Questions on the addition subtraction? Okay. What happens? This is also a fun one. When we move to this next one, I want to know the area of this square. How would we calculate the area? Length times width, so I would take 7.28, and I'd multiply by 4.6, and I would get, please say I can cheat, close enough. I would get 33.488 units squared. That's what the calculator spits out. Is that the correct answer? No. For the exact same reason that our addition subtraction wasn't the correct answer, to just report what the calculator spit out. We have to now take account for where were we guessing and how does that affect our measurement. We could go through and do the exact same thing we did with the addition and subtraction. It's just a lot messier, so I don't really want to stress about it. Okay. Could change that last decimal. Instead of that being 4.60, we made it 4.69. What happens to our number? It changes pretty significantly. Okay. So we cannot assume that that is a 0. So when we do our calculation, we are again fine to enter it into the calculator as shown, but we now have to report it appropriately. So in addition subtraction, we report it to our least precise place. You'll notice in the blue box, is it saying least precise place? No, it's a different rule. What is the rule this time? Fewest significant digits. So what I need to go through and do is look at my measurements and count the significant digits. How many significant digits in the first measurement? 3. How many significant digits in the next measurement? 2. So according to my rules for multiplication and division, how many significant digits are allowed in my final answer? 2. So I would start my furthest left position, 1, 2. My answer becomes 33 units squared. That is your final answer. Anything other than that, sorry, you're wrong. Yes?
So if that 4 was a 5, would it be 34 units?
Okay.
You round?
Actually, let's see. How about we save that question for this part? But what if you go through a system where you end up having to round? Okay, so if we look at our addition subtraction, where should we be reporting our answer to for that example? We cannot report to that place, so we can only report to, what is that, the hundredths place? Okay. But now, as you addressed, what about rounding? Okay. Is that 3 closer to being a 3 or closer to being a 5? 4. 4. Okay. Well, is it closer to being a 3 or a 4? 5 is kind of a nasty one to get because that's dead in the middle. Okay. What if it had been 6? Is it closer to being a 3 or closer to being a 4? 4. So what should we do? We would round the number to 1.34. So what do we do when it's a 5?
Nothing.
Okay. 2 choices. Leave it alone or round up. Okay, which one is it? Completely arbitrary, decided by some random person saying this is the answer, this is the way we do it. Okay, believe it or not, depending on the class I've been in, I've had both answers count as correct. What do we count? Round up. 5 or larger, round the previous number up. Okay? 4 or smaller, keep it as is. So what happens with our multiplication division? 7.8 units times 4.68 units should get us how many sig figs in our final answer? 2. We underline our 2 sig figs, our 3 and our 6. We look at our first insignificant digit, and we decide its relationship. 5 or larger means round up. Our answer becomes 37 units squared. Okay. How many of you are like, cool, I like this is easy? Really? Wow. Okay. The rest of you are like, this is not cool, I don't like this, I don't want to do this. Sorry, you have to do it. Okay. Which, to that extent, I would say, take this slide, commit it to memory. This has your rules on it for what happens with your addition subtraction, what happens with your multiplication division, and it gives you your rounding rules. The one thing it is missing are your sig fig rules, okay, which I think I've got on a different slide. You need to have this memorized. It is of critical importance for our Unit 1 exam. It will show up again on the final. If you have to take 151 or 152 at this campus later in your life, they will beat sig figs into your head by removing all of your points. It's kind of how it works. Okay? I'm not quite so strict. We'll talk about it when it's important, and then we'll address it. I just kind of accept it as we move through. Okay? Don't give me a stupidly large number. Don't give me a stupid few amount. Questions? Okay. When are we done? 15. Okay. So take a swing at some practice. Yeah. There are all our answers. I'm a math whiz. I actually cheat and write the answers in the lower right-hand corner. Yeah. Depends on the slides you got. So, questions about any of those? How are we with 1, 2, 3? 3? What's the end?
I just earlier because I had the trouble with when to drop off that last insignificant digit, and that's at the end, right?
So when you do your calculations, you do not lose digits until you're at the very end of your calculation. So if you're given however many billion sig figs, you have to use however many billion sig figs until the very end of the calculation when you're told, or when you go back and say, well, I'm only allowed to use 1. Okay? It's fine. It's the way it works. But you carry them all the way through your calculation until the very end. Then you make your judgment. Okay? What is an interesting feature of question number 3? How many sig figs do we have in our answer?
3.
For question number 3?
Oh, I'm sorry. I'm sorry.
I have 1, 2, 3, 4, 5 significant digits in the final answer. How many significant digits do I have in my calculation? This first one has 5, but I'm not quite sure where you got the 4 from. There's 3. This one has 6. How did I end with 5 significant digits? Not quite. Not quite. What do you mean it doesn't matter?
So the lowest decimal points is like the way I had it is 0.09. So you just do.
Exactly right. It's based on the precision, the least precise value. That's what determines your number of digits that you can use at the very end. So when you do addition, what can happen to your number of significant figures? It can increase. And depending on your calculation, it could increase a lot. All right? If we look at the next one, number 4. How many people got 454.0? Anybody get something different? Stop lying to me. I talked to like 5 of you that did not get 454.0. 4538. Point. I heard a 7. We'll just leave it at that. Meters. That's a meters. Cubed. Why was that not the correct answer? And multiplication division, I'm only allowed 3 sig figs. If I underline 4, 5, 3, I'm allowed to keep. The 8 larger than 5 means I need to round. And so the natural tendency that most people would go is 4, 5, 4. Say, but I can't have another significant digit, so I'm not going to include the 0. It's now 454 meters cubed.
But it wouldn't, but it's not 4,000.
But then it's not 4,000, it's 400. So what do we need to include? We need the 0, but the 0 can't be significant.
So no decimal point.
Don't include the decimal point. The 0 is not significant. No ambiguity. Sort of, I guess. Next one. Everybody get 0.03 liters? Okay. What's interesting about what happened with that one? How many significant digits in my answer? 1. How many significant digits did I start with? A lot more than 1. Okay. What's an interesting feature of subtraction? You can lose significant digits, which means when we're doing our experiments, particularly things where we're going to subtract the mass of objects, we try to make sure that the difference in mass is as large as possible so that we can keep as many sig figs. If those two values are very, very close, we lose significant digits, and we end up losing meaning behind our calculations. Okay. Last one. The only reason I threw that last one on there, what's kind of goofy with that one? 2 different units. Okay. Are we allowed to use 2 different units in multiplication and division? Yeah. Addition, subtraction we can't. Division we can. What does that mean? We just have our units divided by each other at the other end. Okay. A better way to format that answer, which will become relevant as we move through the semester, would be 0.0454 grams over centimeters cubed. What number should I put in front of centimeters cubed? 1. Why? If it's not 1, if it's anything other than 1, it changes the value of the 0.0454. Okay? So we can put 1s in plate in pretty much wherever we want as long as it doesn't change the value or the meaning of what we're working with. Questions on our sig figs?
So, I thought, well, like, with multiplication and division, I thought it was just to report to the lowest numbers. No?
The smallest number of sig figs. Okay? So in this one, there are 3 sig figs. 3 sig figs in the answer. Not the place.
How big is this on the desk?
Sig figs is massive for unit 1, relatively minor for everything else. And